Hello there, my name is Charles Wasfani Msipa. Welcome to another presentation on computing derivatives. This is a presentation based on your assignment 3, which you have already handed in. I would like to discuss here how you are supposed to present your solutions, compile your solutions for your assignments, because some of you write solutions which are not communicating at all, and they are very difficult to see what are their lines of thinking. So let's start this way by looking at the first exercise, which we all know that here we're required to determine the first derivative dy dx. Now by now, assume that you know all the basic rules of differentiation, which let's say power rule. Let's say we're given y is equal to x to the power n. So we know here that the derivative of this is n multiplied by x to the power n minus 1. And the other things which are assumed here, by now you must be knowing what's the standard derivatives of trigonometric functions. Like for example, I expect all of you to be able to, when I say what's the derivative of cosine x with respect to x, you give that is minus sine x. So now, by now, we're not using the first principles to compute this, we're just using these rules. And in addition to that, we've got the product rule. Based on what I've observed in marking your assignments, I think most of you, they don't really get the idea when to apply product rule. When is it not really advisable to apply product rule? The same applies to the quotient rule. So before we go very, very far, I would like to emphasize here that these two, the product rule and the quotient rule, I would like to talk in simple words and say these were made, this product rule, quotient rule, were made only for a product or a quotient of two functions, nothing more. If you have got more than two functions involved, then you have got to resort to what we call logarithmic differentiation. And for those who haven't looked at the presentation, in your additional resources, study unit number 2, the resource number 8, which is a video presentation entitled Logarithmic Differentiation, there I explain clearly how, when, and how do you apply the logarithmic differentiation. Okay, that means, so now let's come to solve these problems. For in this case here, for 1-1, let me write here solution. So like I told you before, if you are given a exercise like this to find the derivative, I advise you to rewrite the exercise which was given exactly as it is, and then when you start writing your solution, it must be seen where are you, from what are you developing your solution. So in this case here, I would write here dy dx. Now I'm talking about derivative of all of this expression. But as you can see that we've got two functions here, which are y is equal to x, and another function which is y is equal to sine x. So we've got two functions there, which is the situation which fits very well the product rule. So showing our working, we would write the following. In this case, we would write here derivative with respect to x, in this case of the first function, in this case which is x, multiplied by sine x plus x, in this case multiplied by the derivative of dx of sine with respect to x. So by writing that, I'm actually here mimicking our product rule. And it is important to write in such a way that it's very clear in communicating what exactly you are going to do or what you're intending to do. So there we've expressed that we're going to apply the product rule. Writing here, I'm just writing to emphasize that, but it's not necessary to write. But if anyone who's marking your work knows product rule, you see that you're applying product rule here. So what we have here, I think you can see what we have here is dx, which is clearly equals to 1. So in this case here, we're going to have here 1 multiplied by sine. Obviously here, 1 is not very necessary to write, but I'm just writing to show you where we arrived from that differentiation, plus x, and now the derivative of sine is cosine. So multiply here by cosine x. So this exercise doesn't need a lot of simplification, just simple to write here sine x plus x cosine x. Then we're done. Now, what is not acceptable, which I've seen some of you doing, is you are given an exercise like this, then you write on your answer sheet, you just write 1.1, and some of you write very, very badly, say 1.1 equals 2 sine x plus x cos x. This is correct. It could be wrong. Sometimes you can make a mistake in the differentiation, but writing this only doesn't really communicate very well that you have used the product rule. If it's correct, maybe it's fine, but if it's wrong, then one cannot read where exactly your mistake is. But this expression here, expressing this way, saying 1,2 equals that, I think this is false, and you cannot communicate a solution for mathematical exercise this way. This guys is very, very bad. I think this is the worst case. The other situation is when people write something like this. You don't write the exercise which was given. You just write 1.1 dy dx equals, you write that answer there. Even if the answer is correct, but I think your lecturer or your examiner wants to see how you are arriving at the answer. So it will be very, very nice to just to present dy dx equals to sine x plus x cos x. What I'm trying to emphasize here, guys, please show the steps for your working, so that even if at the end you end up with a wrong answer, but you have shown your lines of thoughts, you will get part marks. But if you end up with a wrong answer without any kind of working shown, obviously then you are going to lose 100% of the marks. I hope that is understood. Now let's get to the next exercise. Now in the next exercise, you can see here we've got quotient, and as you can see, we've got two functions there. The numerator is y is equals to cosine 2x, and the denominator is y is equals to sine 4x, and you've got two functions here. This is exactly the situation which needs us to apply our quotient rule. So just briefly, let's remind ourselves what the quotient rule says. Let's say D there is an operator which says we're differentiating a product of two functions u times v. What we know here, this should develop as derivative of u multiplied by v plus u multiplied by the derivative of v. That is the product rule. Maybe some of you want to express it more explicitly. Let's say we're saying the derivative of f of x multiplied by g of x, and obviously here differentiate with respect to x. Here, when I'm writing like this, I'm not really worried about the independent variable for u and v. Obviously, it must be same independent variable. But when you put it explicitly like this, so know that the function depends on x. It could be dependent on x or on t. Here, we've just expressed that the derivative of that with respect to its independent variable. So now, what is going to happen now here is going to be df with respect to x multiplied by g of x. Sorry, what I'm doing here, I'm actually talking about the product rule at the moment. Then let's say plus f multiplied by g of x over with respect to x. That's what product rule will say. Now, in the case of quotient rule, we would say, let's say you've got d of u over v, and then what will happen here, we would say du multiplied by v minus u multiplied by dv all over v squared. So applying the same kind of thinking there, we can also write this quotient rule explicit this way. Then we just follow this formula, we get our quotient rule. Now coming to apply this quotient rule on this exercise, what we now do, or in this case we assume that okay, the exercise is already written there. Now for our solution, and we're clearly developing our solution from there, then we write dy dx, and then this, what you are simply saying, meaning you are saying or differentiating this quotient cosine 2x over sine 4x. Now applying the rule as it is there, then what would have? We would have the derivative of the numerator, which is u, in this case, that will be minus sine 2x multiplied by 2, which is the derivative of the argument of cosine here. So we can insert 2 here, then multiply by sine 4x minus the minus, which is the formula here. Then in this case we're differentiating the denominator, and then the denominator is the derivative is cosine multiplied by 4, which is the derivative of the argument there. So what we're going to have here, we're going to have 4 cosine 2x, which is our u, multiplied by the derivative of v, which is cosine 4x multiplied by 4, all over cosine 4x squared. Then rewriting this will be without the brackets, we can now write cos squared 4x. In the numerator, we can see that we've got a common factor, which is 2. Then we can write the 2 in brackets minus sine 2x sine 4x minus 2, or we can just select minus 2 as a common factor. Then we've got plus there and plus there. Then this will be cosine 2x cosine 4x, and then the exercise is done. As you can see, I think no one can doubt what I'm doing here. It's very clear that we're using the quotient rule. So I hope this is clear, and you can some of you can now easily do that. What I highlight here, what I saw most of you saw here, I differentiated cosine and got minus sine. I multiplied by 2. Most of some of you guys, you are forgetting to differentiate the argument, and that is very, very important. Let's just focus on that a bit. Remember, if I give you a function, let's say is function y is equals to f of a certain argument, let's say u. It could be that u is also a function, and it could be u being a function of x. That is fine. That's not a problem. So obviously, if we're dealing with a composite function like this, we know that we need what we call chain rule. So, but given a function like this, in order to differentiate accurately, you must understand the following. The function here, function f here, could be anything here. It could be a polynomial, or just write polynomial. It could be a trigonometric function. It could be exponential function, logarithmic function, and so on. And obviously, these types of functions is a finite number. The rest, if the function, this function is not any of these, maybe it's a combination of these, maybe being added or multiplied or divided. That's it. So when you've got a function like this, you should understand that here we've got what I can call the argument of the function f. In this case, I will read this as y. The function y is equal to f. Then this one, I would like to call it here the leading function. The argument is also a function. It could be, in its simplest form, it could be just x. In this case, a function y is equal to x, which is the identity function. That is in its simplest form. Otherwise, it can be any function there. For example, we could have y is equals to e to the power sine of x squared. So actually what we've got there, we've got the argument of e being sine, which is a function, and argument of sine being x squared, which is also another function. So please, when you are going to differentiate this, please know what you must know this clearly what you're supposed to do. If you immediately say dy dx or whatever independent variable you're using here, you must immediately reflect on what is the immediate derivative of this leading function. Like for example, in this case here, if I was doing this function, if I say dy dx, the leading function is e, and what we know is that the exponential function, when we differentiate, it bounces back exactly as it is, retaining the same argument. So the argument of e, I can simply say the argument of exponential function e is e. So it's going to be e, retain the argument that. But that doesn't end there. You must multiply by the derivative of the argument. In this case, you must multiply by the derivative of sine x squared with respect to x. And after that, you are differentiating, you're going to call upon the immediate derivative of sine, which will be cos. Then it will be multiplied by the derivative of the argument of this sine, which is derivative of x squared with respect to x. So you keep on doing that. That's exactly what we call chain rule. So what's going to happen here now, we're going to have the immediate derivative of e function, exponential function, which is that, multiplied by derivative of argument, derivative of sine, which is cos, and whenever you differentiate the function, you retain the argument, so it's cos of x squared. Then multiply by derivative of the argument of this sine, then you get here 2x. Then you've completed the differentiation. So what I was trying to emphasize is that most of you, when you some of you, not really most of you, some of you, when you differentiate here, you forget to differentiate this function here as an argument. So say it's simple. If I'm given a function to differentiate, I will always differentiate, find the immediate derivative of the leading function, retain the argument, and then multiply by the derivative of the argument. So there's no differentiation which is complete before we can see the derivative of the argument. I hope that message is clear. Okay, let's move to the next exercise now. Now, in this exercise, what we have, we've got the exercise actually is giving us quotient both sides here, and what we can see in this function here, we've got one function here which is ln x, another function is cosine that, cosine 3x, and we've got another function here which is x, and lastly we've got 4 functions there. Remember, I said product rule and the quotient rule, they were both made for only 2 functions. In other words, if I'm differentiating a product which involves 2 functions, comfortably I can apply the product rule or the quotient rule, depending which is the case. But if you try to apply the product rule here, If you like to be clumsy, if you like tedious work unnecessarily, then apply the product rule. You will see in your assignments, most people here apply the quotient rule. The exercise was so long and tedious and difficult to follow, but I ended up giving people all the marks. But what it tells me, the message I got is that you haven't engaged logarithm differentiation and you haven't appreciated its value. So now let's try to see how logarithmic differentiation can avoid us working unnecessarily. Like, for example, let's write here solution. There is my exercise which was given. Then the first thing we will do here is to apply the logarithm function on both sides here. On both sides. There are some people who are aware that they are supposed to apply logarithm function here, but they applied it on one side. By so doing, violating the basic rule of equations. You do whatever you do on one side of the equation, you must do on the other. Otherwise, the equation will not balance. So then we're going to say ln y equals to ln of this quotient here, which is ln x cosine 3x over x sine 3x. Actually, this exercise, I'm not really very fond of. I noticed this thing very late. I'm not fond of this exercise. The reason why is not as complicated as it looks. There are actually 3 functions instead of 4. Why I'm saying so? Because we could reduce this to 10. Because of that reason, I'm not going to do this exercise here. What I'm going to do, I'm just going to modify it a bit, just to get it a little bit more complicated so you can see the whole story very well. Let's take y equals to ln x cosine 2x over x squared plus 2x multiplied by let's say 3 to the power sine x. Right. So now we've got 4 functions, and you cannot simplify this to 3 functions, nothing like that. So, but that explanation will serve to solve this, to explain the situation here and even there. So I'm only going to do this one. So what we do here now, we'll say now let's apply ln on both sides, again on both sides. So that will be ln of ln x multiplied by cosine 2x x squared plus 2x in brackets 3 sine x. Now, once you've applied ln on both sides, please, on this quotient where we've got a lot of factors there, you must apply all the possible properties of ln and make sure that this expression is in its simplest form. In this case here, what we do, we would first of all apply the property. We say ln of m over n is equal to ln of m minus ln of n. And we also need ln of m times n, which is equal to ln of m plus ln of n. So applying that, we're going to have here ln y equals to ln of ln x times cosine 2x. I'm loosely using the brackets here, but I hope you know that this should be strictly an absolute value because ln does not take negative arguments. So then then we say the ln of x squared plus 2x multiplied by 3 sine x, and again this is in brackets. So as you can see at this stage, we haven't exhausted the properties of ln. We still have a property of ln to apply here and there. Then we're going to now write this as ln of ln x plus ln of cosine 2x minus ln of x squared plus 2x minus ln of 3 sine x. Notice one thing here. Up to this point, we haven't done any differentiation. What we're just doing here, we're writing this expression in its simplest form. Now, when you get here, you can see we still have got a property of ln to apply here. So please don't start differentiating. And when you start differentiating, at any stage you start differentiation, please, it will be differentiation on both sides, not on one side, then in the next step, differentiate the other side. Then your whole exercise is starting to be wrong. So writing this, finally, I think we'll write this as ln y equals to ln of ln x multiplied by ln cos 2x minus ln x squared plus 2x minus ln 3. Notice that this is a constant, ln 3 multiplied by sine x. Here we've used this property which says if you've got ln, or let's just say log m to the power p, this is equals to p log m. But because multiplication does not worry about the order, then that's how I wrote it here. Now, at this stage now, we are ready to differentiate. Now we're ready. We're really ready to compute our dy dx. We're ready for dy dx. But as you can see here, there's no more y here. We've got ln of y, which means at this point here, that's when we start also applying our implicit differentiation. So we've got to find dy dx here implicitly. So then, I hope by now you know how to differentiate ln. And the derivative of ln, I think, is one of the easiest derivatives to determine. If you've got ln of, let's say, u, if you look at it again carefully, you will see that the derivative of this with respect to, let's say, u is a function of x, this will be simply equals to 1 over u, which I can just simply call 1 over the argument of u. And we said it before, any derivatives comes multiplied by the derivative of argument. So here it will be multiplied by du dx. So then that's what we're going to do there. That's what we're going to do here. There. We're going to be just simply doing our usual differentiation of function sign without ln, because this is a constant ln of 3. So now differentiating, we would write 1 over y dy dx equals to, there it will be 1 over ln. In this case, ln here is the argument of this leading ln here, multiplied by the derivative argument. In this case, our argument is x for ln, in this case here, which would mean that if you've got x there, here we'll end up having dx dx, but that what is 1, and we normally don't write that 1, but we need to understand that 1, there's 1 there. But in this case here, we'll have 1 over x for this part, and for that part we've got 1 and we don't write it, then plus 1 over cosine 2x multiplied by the derivative of cosine, which is in this case minus sine, or that will be minus 2 sine 2x. And please, you cannot leave this like this. Once you leave that this your work like this, then this becomes a bit, causes some bit of noise here. So what to avoid that, to show that you're multiplying, please put this sign here in brackets. Then it's easy to see that we're multiplying that. There's nothing confusing. But I'm emphasizing that just for easy reading of your solution. Then coming there, is we have minus 1 over x squared plus 2x multiplied by the derivative of the argument, in this case which is going to be 2x plus 2 minus the derivative of sine is cosine multiplied by this amplitude here, which is a constant. Then it's just going to have ln 3 cosine x. Then at this stage, there's no more differentiation to do. What you need to do now is just to reorganize this exercise and write your solution in a more compact way. So then we now write, first of all, notice that we need dy dx. We need to make dy dx subject to the formula. So immediately we can indicate that you're going to multiply both sides by y, both sides of this equation. Then we're going to end up here with dy dx equals to y brackets, simplifying this, we're going to have y 1 over x ln x, and there we're going to have minus, if you check properly, you're going to minus 2 here, and then you've got sine over cos, which is tan. Then you can simplify that and write that as tan 2x, then minus, there we've got 2x plus 2 over x squared plus 2x minus ln 3 cosine x. Then your exercise is completely done. So I hope you followed the process. Please notice these are the most important steps. You have got a quotient or a product with too many factors. By too many in this case, I'm referring to anything more than 2, because for 2 we've got product rule or we've got quotient rule. Apply ln on both sides. Once you start applying ln on both sides, anyone will notice that you are going to do what we call logarithmic differentiation. Then the first thing to do is you must exhaust the application of all the properties of ln, of logarithms, and then when you've exhausted that, then you differentiate very, very easily. Like the derivative of ln is always 1 over the argument multiplied by the derivative of the argument. That's just so easy. So then I'll then leave this exercise for you to do if you didn't do it correctly at the beginning, or if you did it using quotient rule and it was very tedious. Try to see how do this using logarithmic differentiation and see how you cut down a lot of working, and you have a kind of a nice presentable solution. Now coming to number 3, in this case here we've got tan second function, now the inverse of the function tan. I hope when you get to this, for example, you've got inverse of tan, there you've got inverse of cosine. By this time you should have looked at my presentation on our additional resources, which says bonus from implicit differentiation. What did I discuss in that presentation? For example, let's say we've got here function y is equals to tan. Let's say tan x. We all know that the derivative of tan x is sec squared x, of course multiplied by 1. Now what we have there, we have y is equals to second function tan. Now that we know the implicit differentiation, what we do, we can simply apply tan on both sides here. And once we've done this here, we're sitting with a function and its inverse. We know that that's going to give us, that will be an identity function. In this case, we're going to have x here. Now, if we do this differentiation now, remember here we're looking for dy. We're looking for dy dx. Now here we've got a function, implicit function involving y. So if we differentiate this thing, we're going to have dy dx. So what we can do now, we can now say sec squared y, that's the derivative of tan. Then it must be multiplied by the derivative of argument, which is dy dx. And then in this side we're going to have dx dx. In other words, this is the derivative of the argument. Now making dy dx subject to the formula, I hope you can see that we're going to have this as dx over sec squared y. I'm leaving it as it is here so that we can see that we're talking about the derivative of the argument of the inverse function there. But writing this thing more nicely, I'll write it as 1 over sec squared y multiplied by the derivative of the argument. And then when we look at this function, the derivative now, it comes in terms of x and y, but the function was originally given in terms of y, in terms of x. So we need to substitute backwards and get this expression in terms of x. But what do we know? We know that sec squared is equals to 1 plus tan squared. So if we check what we have here, tan squared, tan is x. So what we're going to have here is 1 over 1 plus x squared. Now I'm going to refer to x here as the argument. So it's 1 over 1 plus the argument squared multiplied by the derivative of the argument. If you can read this to yourself this way, that the derivative of the second function tan is 1 over 1 plus the argument squared multiplied by the derivative of argument, then you are not going to make a mistake when you differentiate the following. So what we're going to have here now, we're going to say df dx. According to what we've just seen here, the derivative of second function tan is 1 over 1 plus the argument squared multiplied by the derivative of the argument. So what we're going to do here, just simply going to say 1 over 1 plus the argument, in this case, which is x, the square root of x. This must be squared, then multiplied by the derivative with respect to x, of course, of the argument. Then the question is now, do we know how to differentiate y is equal to the square root of x? Remember, the square root is the power, which is power half. Then applying our normal power rule, we know that this dy dx is going to be our n, which is half, multiplied by x to the power n, which is half, minus 1, and then this is 1 over 2, x to the power minus 1 over 2. Then simplifying, this will give us 1 over 2 multiplied by 1 over the square root of x. Remember, when you've got x to the power minus n, this is 1 over x to the power n. So our power half, we translate it back to the radical sign. So now, which means here the derivative is simply 1 over 1 plus x, because we're squaring here the square root of x, multiplied by 1 over 2 over 2 square root of x. Simplifying that, writing nicely, you write that as 1 over 2 square root of x multiplied by 1 plus x. That I think it's best to leave this expression this way as 1 over 2 square root of x, for that. Some people remove the brackets here, then you end up with okay, I don't know, whereas you say funny, but it becomes clumsy. Then somebody writes something like this: you've got the 2 to the power x to the power half plus the 2x to the power 3 halves. I don't know which one you see looks appealing to you, whether to write it this way or that way, but I would prefer to leave it this way because it looks to me more compact and very easy to read rather than that. But I'm not saying this is wrong, but I'm just saying in terms of easy reading that. I hope you got the explanation on this derivative of time. So in my presentation also, I present work related to this kind of derivatives. Here I just repeated it because I wanted to make this explanation correct. Otherwise, I could have just referred you to my presentations, which are online on our e-tutorial site. So now I'm going to leave this one for you to do. Here the exercise I'm going to leave one to do for you to do, and just right here, do it yourself. Right. So again, in this situation here, please, there are two functions. Don't unnecessarily apply ln. Actually, once you have learned ln differentiation and you know all these the rules like product rule, quotient rule, it's also part of your learning to get to a situation where you can judge for yourself that in this situation I need necessarily to apply ln differentiation. In this one, no. Don't just unnecessarily apply ln, or where ln is not really where product rule, quotient rule is not really working fine. You need ln. You must apply ln. So there are a lot of guys who got 100% in the assignment, and they used quotient rule for that ugly quotient involving more than 4 functions. Under normal circumstances, I would have penalized you for not having able to judge that the situation is not very, very conducive for quotient rule or product rule. But otherwise, I just pardoned you and accepted the answer as it is. But please learn when to use and when not to use logarithmic differentiation. And also now I would like to say thank you for listening. If you've got any comments, you can post your comments to my email, or otherwise I'll meet you again in the next presentation. Thank you.